Good, it is recording. Okay, so I will now correct my error of including too much stuff last time by finishing up the heat engines thing, which we didn't have time for. First, I want to do just a quick review of some of the things we discussed last time. So we did this potential energy stuff, then we did this density and center of mass and moment of inertia, and this was kind of the most important section from last time in terms of things that we're going to use moving forward. It's like deriving that hydrostatic barometric equation at the end. This is just kind of a cute thing. So I want to review this because this will be important. Then I'll tell you about heat engines, like the Carnot engine. I'm going to have a quick interlude to introduce probability because we're going to change tracks today and switch from applications to science to doing probability theory. And then we'll start the probability proper by talking about what continuous random variables are. And that'll launch us in probably for a couple more meetings. Why do I have 54 up here? This is session 55. Sorry, 55. But yes.
So now I have a thought.
Yeah.
It doesn't look like you have a lot of acts here. Is it going to be 2 hours?
We'll see. Maybe. Depends. There's some challenges, so that might eat up a couple minutes. I don't know why. Do you have something else you want to do at the end? Like you want to wrap up earlier or something?
No, I was just curious because I saw 2 acts. So I'm like, is this going to be short, or is the heat engine going to eat up 45 minutes?
Yeah, it depends on how much we talk about this. This could be a bit long. This is a very long topic, heat engines. If you take a physical chemistry class or a thermo class, you will spend at least 1 or 2 weeks talking about heat engines and the Carnot cycle. So one could spend a lot of time on that. It's perhaps irresponsible of me to do that now since the focus is mostly calculus and not thermodynamics, but I still want to give you a taste. And this should be really the main gist. But we'll see. Yeah, it might be an hour and a half or something, or maybe an hour and a half, end early, but that's all right. I've been busy reading master's applications, as you know, so it's eating into my time to write slides.
Yes, that is a higher priority than this is. Whatever this is basically a hobby.
Well, yeah, but I don't know. I care about you more than I care about the master's students, so I don't know if my priorities are correct. But
that sounds mismatched.
Yeah, whatever.
Oh, as you said, you don't know if your priorities are correct.
Yeah, I can make my priorities whatever I want, but okay, let's quickly review, I think just a one-slide review of kind of the main stuff from the second act last time. So I want to write these 3 kind of equations, and you'll notice a pattern going up, which is going to generalize when we discuss probability. But first, let's just talk about what we did last time, and I'm going to do it just in the one-dimensional case for simplicity. So what I invite you to think about here is some rod, which I'll draw. Maybe I shouldn't draw it on the same axis. I'll draw a rod in blue, like this, which we think of as being effectively one-dimensional, and maybe there's some places where it's not very dense, but then maybe in the middle there's this very dark coloring where it means the rod is denser or something, and then, I don't know, maybe it goes back to being less dense at the end. And you ask, how do I characterize the mass distribution in this rod? And as we saw, the right answer was to think of a linear density function, lambda of x, which is kind of small where this guy's less dense, then this gets bigger where it's very dense, and then it can maybe kind of tapers off and goes back to 0 where it's less dense again as a function of x. And then this density function, so again, the units of lambda, I'll use brackets, should be something like kilograms per meter. So this is something that you multiply by meters to get a mass. And then we saw we could define various properties via integrals of this lambda. So the point of last time was if you chop up these regions into little pieces like a Riemann sum or an upper or lower sum, the way that we're used to before, you might say something like each of these are a contribution of a little mass lambda at a point xi times the width delta xi, because that gives you the mass of this chunk. And then adding up all those lambda of xi's at delta xi should give you the total mass. Or said differently, if you take the limit as the delta xi's go to 0, this thing should turn into an integral if, I don't know, I made this on minus L to L for some reason, but if you take that limit, then this thing becomes the integral of the density function with respect to x. So this is something which you might call the total mass or total content. But then we saw there were higher integrals you could do. So if you wanted to not just add up the density of each chunk, but take a weighted average of the locations of the chunks, where the weight is the density function, then this is a sum which is going to add up locations on the rod with preference, with heavier weight, for locations associated to more massive chunks or denser parts. So this is sort of, if you kind of ask the question, where would I need to put a little, if I had some guy who was trying to balance this rod on his finger, right? The question of where should I put my finger to balance the rod? That is the question which is answered by the center of mass, right? So the center of mass is that location where you could put your finger under it and just balance the rod perfectly under the center of mass. So as we saw, that also has an integral expression, x center of mass, which is an integral of x times the density. We might call that a weighted average or something, or a first moment, as terminology we'll see soon. And then we had this argument, this very clean argument, I think, for writing the kinetic energy of some object which is rotating, which we proved is 1/2 I omega squared, where we did this split of the energy into the geometry in I and the dynamics, the rotary motion in omega. And we saw that the thing which popped out naturally in that splitting was this thing called the moment of inertia, or second moment of inertia. And that thing is the integral of x squared times the density. So if you're trying to interpret these, you might say that this thing is something like the spread, right? Because this thing becomes larger if you weight more heavily masses that are far away from the origin. So the size of this thing tells you basically how much of this mass is distributed far from the origin, right? Like a
Question.
Yeah.
Does moment of inertia have units?
Yes, it does. We can see what they are from looking at this, because moment of inertia is adding up a length squared and then times a mass. So this should be in kilograms times kilograms times meters squared. Yeah. So equals kilograms times meters squared. And now you see the units for energy work out, because omega is in radians per second squared, but radians are dimensionless. So this is kilogram meter squared per second squared when you multiply by the omega squared, and that's joules, right?
Whoa.
We're in good shape.
One of these days I'll be up. It's strange to think about units where all the powers are positive.
Oh yeah, like products of quantities, like a kilogram times a meter. Like, what is that, right?
Yeah.
Yeah. It's less intuitive than fundamental units, but as you do
Is there intuition to be found, or is it just accepted?
Yeah, it depends on the context. In the most general case, the only way you can interpret that as this is a number which is a product of two quantities, one is a mass and one is a length. Often that's the best you could do. But sometimes, especially in electromagnetism, when you have units like farads, like capacitance, and units of inductance and things like that, sometimes you can have some physical intuition for what a product of two things should be. Like, that, I don't know, just using a simple case is the electron going through a voltage difference, right? You know that, this charge times a voltage is supposed to be an energy, right? So this is why the units of electron volts, right? Electron volts are units of energy, because this thing is a product of a charge and a voltage, which is in units of joules per coulomb, right? So the product EV has a very natural interpretation, like, oh, I think of an electron going through a gradient or through a gun that accelerates it or something, and that's an energy. But those are special cases, though. I agree. In general, interpreting something like a kilogram meter is trickier. Sure. Good question, though.
Okay.
Other thoughts on this quick review?
No.
Okay. All right. This same structure we will see later today, and these are going to correspond when we get to probability distributions. Mass is going to be total probability, and then this weighted average is really just going to be the mean of a probability distribution, the mean, or we sometimes say expectation value. And this thing called the spread is going to be something called the variance or the second moment. And that's actually why we call moment of inertia. The word, you might think, what the fuck does the word moment have to do with this? It's just telling me how far away the mass is from the origin, right? It's because this formula looks exactly like the formula for the second moment in probability, which we'll see today. So that's
So I have another random thought.
good.
I have no idea what standard deviation is actually supposed to mean.
Yeah, exactly. Because how was it probably taught to you when you learned standard deviation in school?
Here's a formula, solve things.
Yep, fucking yes, absolutely. Here, maybe not today, probably next time, but we'll start it today. There's a rigorous definition of standard deviation, which we'll see, and once we define what the expectation value is via an integral, the standard deviation will basically be a very nice thing. It's an expectation value of your random variable squared minus the expectation of the random variable itself, quantity squared. So this e doesn't commute with squaring, right? So this is different from this. If you do e of x squared, it's different from e of x quantity squared. So I'll define what this e is, and then the standard deviation is just the square root of this. So as we'll see, this is a very natural definition, and it has to do with that formula that you know, but I mean, this thing is actually much more natural in terms of the integral when you see it. But yeah, that'll make more sense too.
So why did they not just hold off on mentioning it until calculus? If there's no use for it in algebra beyond, hey, it's a thing.
I have that same question about most of the things they tell you in, like, early on math and science classes. I don't know. I could rant about this, but it would not be a good use of your time. Good.
Clap.
Other questions or words that have come up in probability that you want to quickly flag for me to point out when we get there?
Not that I know of.
Okay. All right, good. Well, let's finish the gas stuff first, since that was lingering from last time. So I was trying to convince you that integrals are useful in science, and we were talking about applications of integrals to ideal gases, beyond just proving the ideal gas law. So we got the barometric formula that tells you that pressure drops off exponentially under certain assumptions, and now I want to tell you about kind of like the beginning of modeling engines and understanding how you could do work with an ideal gas. Okay. So first, a review. I had you do this in this nice DC. Well, I shouldn't call it nice because I wrote it. That's kind of self-aggrandizing. On this DC, where you were finding the work done by an ideal gas.
Okay, now I must interject.
What?
Was that a written DC or was that a poll DC?
That one I invented. I've been making up most of them recently.
Q.
Yeah. This chapter, it's not out of Spivak. This chapter has mostly just been shit that I like to talk about, so I'm making up most of the material as I go along, so please forgive the drop in pedagogical quality since I'm just making shit up as I go.
But the more recent problems have been interesting.
Ooh, good. Thank you. I feel nice now. Well, alright, well, I shouldn't I don't know, toot my own horn here or whatever, but okay, good. So in that DC with the piston thing, you remember there was some piston with some area A, and it was supposed to be expanding or something, and I tried to convince you with this picture that if this thing moves by a little height h or something, and the force per unit area, which is called pressure is force per unit area, I tried to convince you that if the gas pushes on this piston and moves it by a height h, then the work that has been done, which we would normally say is kind of like an integral of f dx, we could really think of that as an integral of p dv, simply because the pressure is the force per unit area, but the volume compensates for that per unit area by multiplying by area, right? Like dx times area is dv. So for gases, we do this integral of the pressure integrated with respect to the volume. Which you did. You got this nice formula for the ideal gas, so this one, the case with no van der Waals shit is quite simple. This V should be capitalized. You just integrate, say, the pressure from the ideal gas law, which is nkt over V, which gives you a log. And this just tells you that if an ideal gas expands, the work that it does is related to the log of the ratio of those the before and after volumes. So today we're going to try to think about this more geometrically. So we know from last chapter when we learned integrals that we kind of at the very beginning of the day, we thought of integrals.
Random thought.
Yeah.
Should that be a capital V or a lower V in the formula you have there?
This should be a capital
Or
V.
the DV. Okay.
Yeah, sorry, this is a typo.
Oh, that's what you did. Okay, I'm dumb.
Yeah, no, I did it and then I erased it because I'm silly.
I was like, wait, something isn't.
Yeah, sorry.
Because, as you were saying.
Good. No, please do interrupt if there's typos though. This is good. I have a lot more fun with our meetings when when you interrupt me more, because then I don't feel like I'm boring you. But okay, good. So when we first introduced integrals, the idea was that they're supposed to be computing areas under curves. And now we're starting to use integrals in ways that don't immediately seem obviously related to areas under curves, because this thing just looks like some work integral, a force over a distance, or a pressure dV. But today we're going to reverse the process and say, okay, now that we've used this scientific application where the integral is computing some work, can we go back and think of this graphically, which will be helpful when we do the Carnot engine, as the area under a curve in the pressure volume plane. So I ask you now to think of the x and y axes as not x and y, but volume and pressure. So this is what we would call a phase space. By phase space, I just mean it's some plane where a point in the plane we're not thinking of as an actual physical location in space. It's not like a point on a table, x, y. We're thinking of one point in this space as corresponding to an entire configuration, an entire specification of the ideal gas parameters, right? So one point in this plane is an actual like box of an ideal gas with a given pressure P and a volume V. And as you move around in this plane in different directions, you're changing the volume and the pressure. Okay, so I mean, maybe that's kind of obvious, but I just want to be super clear about this point, that points in this plane are different configurations of the gas. Okay, so with that understanding, you could think of this process of, say, maybe we're, in this case, what I've drawn here is compressing it. So we start at some big volume and then move in phase space towards a smaller volume and a higher pressure. So this is compressing the gas. This is a compression. And then you can think of the area under this curve. Well, this time we should really think of this area as being negative, because you know from integrals that when we go from right to left, right, when you reverse the order of integration, you should think of it as a negative area. So what is the interpretation of that? Well, negative work means the gas is not doing work on its surroundings, but I'm doing work on the gas, right? And that's exactly what you'd expect for a compression, where you're reducing the size of this because you have to squeeze on a balloon, for instance, to put work into it to compress it. So anyway, so it's sorry if I'm belaboring this point too much, but just to emphasize, we're going to think of motion in a PV plane, and the area under the curve in that that planar motion is now a work, which is positive or negative. Okay, good. Ask me questions on that.
I do not have any questions on this. This is still reminding me of, you mentioned earlier that it seems a bit confusing relating work to the area, and I think it makes sense to me just because of the original gravity versus energy examples.
Ah, good. Yeah. So in those cases, you think of the work as integrating ftx, so it's like integrating a constant over y, so it's like a rectangle or something. Is that what you mean?
Yeah, just, I think that it's clear. Yeah. Why did I questioning tone if it was clear?
I was going to say, why did the pitch raise there by an octave? Okay.
An entire octave. Yeah.
Probably not that much, but okay. All right, so let's say we're happy with that. So now we're going to think about a more complicated thing you could do to the gas, and then we're going to try to imagine that in the PV plane. So let me just give you some context first. So this is something, as I said, you would do in a thermo class, and the motivation for this in a thermo class is something called a heat engine. So the idea of a heat engine is the following. You have some temperature gradient. By temperature gradient, I mean somewhere over here you have this big heat bath. So this is a source of heat which is held at a certain temperature T hot. And then somewhere else you have a bucket of ice or something. So a big reservoir of cold, or a cold sink. So we have a cold sink at the bottom, and we have a heat sink at the top. Heat sink. And the heat sink is at T hot, and the cold sink is at T cold. Now you could ask the very natural question, is there a way for me to extract useful energy from the difference between these temperatures? In other words, can I use this temperature gradient to drive work or do some useful process, like, I don't know, lift a rock or something, like do some, or move a car or whatever, right? That's the purpose of an engine. An engine is supposed to do useful work. And the answer is yes, and a very simple kind of thought experiment way, a simplified model basically for the way an engine which uses this heat difference would work, involves an ideal gas. So we're going to explain over the next couple slides, and we're going to explain it a couple times because I think it's actually quite complicated when you first see it. We're going to explain a series of steps with an ideal gas that will do net work using this temperature difference. So there's 4 steps. The first step at the far left here is called isothermal expansion at T hot. So you should think of that as taking your ideal gas, which is in a box, and you push it up against this heat sink at T hot. And maybe this box can expand or contract a little bit. And when you push it against the heat sink at T hot, this guy is going to expand. So that's what the lowercase q here is heat. So heat enters the ideal gas from the heat sink. And as that happens, the thing is going to expand, which means it's going to push this piston and do some work. So we get some positive work out of it here, right? So here's a net plus, basically. Okay, then what do we do? Then there's a second step called adiabatic expansion from T hot to T cold. In this picture it's TL for low, but I prefer TC for cold. So what does adiabatic expansion mean? Adiabatic expansion means I move it far away. I mean, imagine that this is a larger distance. I move it far away from the heat sink. So adiabatic just means it's not taking in any heat or putting off any heat to its environment. It's just doing whatever with the energy is not going in or out. So I move it away from the heat sink, and now I let it expand a little bit more. And in this step, it maybe increases a little bit more to a slightly bigger volume, but as it does that, no heat is being exchanged with the environment. Okay, so that's an adiabatic expansion, and again, since it's pushing out on the piston at this step, I get positive work. Okay, well, I mean, that can't be the end of it, because if this is an engine, we want to be able to repeat this over and over. So now we have to somehow bring it back and bring it back to the original state, get it to a cold state so we can put it back so it heats up when we put it against the heatsink. So the third step is called isothermal compression at T cold. So now I put the ideal gas right up against the cold sink at this cold temperature, and now I have to put in work. I have to compress it. So I'm going to push on the gas at the cold sink and compress it back. So this is like resetting it, right? If you think of this as I don't know, like a jack-in-the-box or something, I popped the jack-in-the-box up here and it popped out, and now I have to reset it by turning the crank again and rewinding the jack-in-the-box. So I'm putting a minus on here because we lose work here. I have to put work in to recompress and reset the gas. But the point is, as we'll prove, I'll show you later, I have to put in less work here precisely because it's at a colder temperature. So we'll see that. Then the final step is again an adiabatic compression. So this is again no heat exchange with the environment. I'm going to push it a little more, compress it a little further when it's not touching the cold sink. So again, I lose some energy there. But the point is that this thing is cyclical, so after this last adiabatic compression, I can bring it back against the heatsink and do this whole thing again. And again, we'll calculate precisely how much work I put in or lose at each of these steps, and I'll show you that the net amount will be positive. But first, okay, so that was very complicated. Is the picture or the caricature of what we're doing clear, and or do you have comments?
It is clear and I do not have comments.
Okay. All right, let's carry onward then. So now let's try to translate that to this PV plane. So I'm going to try to just show the same steps again, but now think about how this guy's moving in the PV plane during each of those legs, right? So the first one, the isothermal at T hot, so that's this first leg at the top. So this is drawn with a nice little hellfire Satan thing here at this hot reservoir. So at this step, where we're moving in the plane is along these arrows going downwards, right? Because the pressure is decreasing and the volume is increasing, right? Because we're doing this, sorry, isothermal expansion. Yeah. So if he's expanding, he's losing pressure and getting bigger. So you can imagine some big area here. The area under this, this one leg is all of the work that we're getting at the isothermal part. Okay, then I take him away from the heat sink, the heat source, and let him adiabatically expand a little more. So now he's going to move along this different shaped leg. Again, the pressure is decreasing and the volume is increasing a bit. Then I bring him back down to the cold sink, and the cold sink is where I have to put in work, so I'm compressing him. So I'm doing some work, which means there's some area. See this lower area down here, I should really count with the opposite sign, because now the arrows on my path are reversed, which means I'm integrating the wrong way, right to left. So this is negative down here, but that's okay. At the last step, then, we just do this adiabatic compression again, which brings me back up to the start. And now I'm up here. So the point I'm trying to make is that the beauty of the geometrical interpretation, the area interpretation here, is now I can see that this thing is going to buy me net positive work, right? Simply because the area of this region is positive. Because these top two legs give me positive energy or positive work because I'm going from left to right. The bottom two give me some negative work because I'm going from right to left. But we can see that overall the top curves are above the bottom negative curves, so we get some work out. So that's the intuition. Okay. Let's see. Wait, did you say something?
No, I was just going to say that this is clear.
Okay, cool. I think I have one more picture of this because I want to emphasize a different thing this time. Okay. I couldn't decide which of these pictures I like better, so I just put in both of them. So now in this slide, I want to emphasize a different part. So this is the same picture. Sorry, it's the same thing I was showing with the same area and the same idea of the heat sink, then pulling them out, putting them on the cold sink, and then pulling them out, and then back again. Now, if we want to prove that this area in the middle is positive, we need to do some integrals, which means I need to integrate PdV explicitly, like with an equation, for each of these legs. Now, I claim we need to first know what is the functional form, what equation does the pressure satisfy as a function of volume on each of these legs. Now, the isotherms are easy, because on these guys, isothermal means these are all happening at the same temperature. For instance, step 1 is all happening at temperature T hot. And we know by the ideal gas law that if this guy is all happening at one constant temperature, this is just what you did on the DC before, right? This means that the pressure is nkBT over the volume, so it's very easy to integrate this from, say, VA to VB and get the work done on leg 1. So work on leg 1 is just this integral, which we've done before. It's nkBT log of, in this picture, I guess, VB over VA. VB over VA. So that's pretty easy. And the bottom isotherm at 3 is also pretty easy. The tricky part is these adiabats. An adiabat is different, and I'll explain this a little more, but not in super detail in the next couple slides. So maybe I'll just ask you conceptually, can you see why we can't apply the ideal gas law and do the same integral on this step 2, which the picture is actually this thing, step 2, which is the picture I just circled? Why can't we use the ideal gas law there?
I believe that. No, thank. Are we assuming that any extra energy is instantly converted to extra pressure? Or extra volume, sorry.
Not. What do you mean extra energy? Do you mean extra energy as this guy is expanding in the adiabat?
I think. I was trying to think about if, like, why this is continuing to expand even after we've taken it off heat.
Mm-hmm. Yeah. That's the key point. That's a good thing to think about, because once you've taken the key thing to recognize is once we've taken this guy off the heat, he's no longer in contact with any temperature bath, right? So he's not being held at a fixed temperature, which means his temperature can change. But if his temperature changes, then that since he's isolated from the environment at this step, adiabat just means no energy is exchanged with the environment. So if I take him off the hot source, he's not going to stay at that same temperature. But when his temperature changes, the energy which used to be stored in the thermal energy of the temperature has to go somewhere. And it's going to go towards putting basically some pressure as he expands a little bit. So I said that sloppily, so let me say it one more time. The reason he changes here at this step is because I took him off the hot source. He's no longer touching the fire. When he's no longer touching the fire, he's naturally going to cool down. But when he cools down, there was energy stored in that temperature, so the energy stored in the temperature that he's losing is going into expanding him. It's doing PDV, basically. Does that make sense?
And so is the problem with this that T is not constant?
Yes, exactly. Yeah. Because when this guy cools down, we can't use the ideal gas law because temperature is now changing as a function of pressure and volume. So we don't know how to do this integral when these three variables are changing at once, right? PV and T. You need an extra equation to figure out what he's doing on the adiabats. So that's why those are hard. And I will actually give you that equation. We could derive it if you wanted, but it's actually kind of a pain in the ass. Maybe I'll just sketch the derivation. But okay, so here's what I just tried to signal to you on the adiabats. So the isotherms are easy because it's just ideal gas law. On the adiabats, there's something more complicated going on. And what you basically have to do is saying, well, you say the total energy change is 0 on the adiabats. And by the first law of thermodynamics, this is basically some TdS minus a PdV. So you have to derive an equation relating the pressure, volume, and temperature on the adiabats that has to do with the entropy of an ideal gas. So this goes back to what we did before with, we don't have to count microstates or anything, but we have to use some similar equations to before. But I think for the purposes of this, it might be more preferable for you if I actually rather just kind of skip that calculation and tell you the answer that you get. So when you do that calculation, you find that on the adiabat, the ideal gas satisfies this equation. Roughly, it's the pressure times the volume raised to some power gamma. And you can actually show that gamma is some ratio. I think it's Cp over Zv. Have you learned what heat capacities are?
I mean, the word makes sense, but I've not learned.
Okay. All right, maybe I won't say more about this then. So you can think of this equation as just saying there exists some constant gamma, which I think is like 7 over 5 for ideal gases or something, and some other constant k, so that on an adiabat, the pressure times the volume raised to that constant gamma equals this other constant k. So let's just assume that this is the case, and if you really want, I can derive it next time. But okay, so if that's true, now what should I do to find the work done on one of these adiabats? So the work done under one of these legs, say it's between initial volume VI and final volume VF. What should I do?
Let's see. I guess we can integrate each side of this equation.
This side. Do we want to...
Well, PV.
Let's see. So
Well,
what we would normally do for the work is integrate P dV. So you say, can we integrate both sides of this equation?
that would not work.
Yeah, I don't think we can do that yet. But what we can do is we can solve this equation for pressure as a function of volume and plug that into the work formula, right?
Sure.
dV. Okay, so if I do that, what do I get by solving this guy at the top?
P equals K over V to the power of something, probably gamma,
Yeah,
over gamma.
it's gamma. Do you not know the Greek alphabet yet?
No.
Sweet summer child. Okay. All right, so knowing that that is the functional dependence of pressure on the volume, now do this integral for me.
All right. we pull out the k since it's constant, and then assuming that gamma is not equal to 1,
which is
we have the big voice from VT, well, VI to VT of 1 over V, I think.
might help to think, just a little hint, this is v to the minus gamma if you prefer.
Yeah, it makes it... I don't want to get integration and taking the derivative confused again. Integration is going up by 1 power and dividing by the new power.
Yes.
Okay, so in our brackets we're going to have v to the negative gamma plus 1 times 1 over negative gamma plus 1.
Good. Perfect. Yeah, so indeed, you can, I don't know if it really matters, but you can evaluate this if you want. It's the final volume to the minus gamma plus 1 minus the initial volume to the minus gamma plus 1 all over minus gamma plus 1. So yeah, it's good that gamma is not equal to 1 because then you get a log or something, but yeah, I think again for ideal gases it's like 7/5 or something.
If it was 1, we could just see that it was k log v.
Yeah.
Yeah.
Yeah, true. Then it would be basically the same answer as the ideal, the isotherms, because they had logs.
Whoa.
Good. Okay. So indeed, if you solve that pressure equation like this and plug it into the work integral, you're integrating k over v to the gamma, which is k times 1 minus gamma, vf to the 1 minus gamma minus vi to the 1 minus gamma over 1 minus gamma. So I'm actually going to do a little trick, which I did not ask you to do, but we can re-express this in a nice, interesting way. And I'm just going to do it on the side, even though I wrote it there, but just to show you what I'm doing. If you start with the ideal gas law, PV equals NKBT. Now, by the way, we have to be very careful about the ideal gas law because the temperature is changing. So I'm not going to apply the ideal gas law along this curve at any points where the temperature is changing. I'm just going to apply it at the two endpoints where I know what the temperature is, right? Because I know it started at one temperature, which was, what was it, T hot or something, and went to T cold or something. So if I only apply ideal gas law at the endpoints, I'm safe. Or maybe I'll call them final and initial or something, but whatever. Okay, so I want to figure out what this v to the power 1 minus gamma is, right? Well, that's pretty easy. Why don't I just divide both sides, why don't I just multiply both sides of this equation, the ideal gas law, by v to the power minus gamma. V to the power minus gamma. Because then on the left side, I have pv to the 1 minus gamma equals nkbt over v to the gamma, I guess. So the left side is the pv to the 1 minus gamma thing that, oh wait, shit, this is not what I want to do. kv to the 1 minus, why am I confused? PV to the gamma is a constant. Did I say something wrong here? Why can't I figure out this derivation? PV equals NKBT, and we also know PV to the gamma equals K. So I should be able to figure out what this thing is. If I multiply both sides by V to the minus gamma, I get this.
If you want to gather your thoughts while I grab my water bottle, I'm cool with that.
Okay, thank you.
I'll be back in a minute or so.
Cool.
There's no writing up. This is strange.
Oh yeah, I erased it so I could redo it in real time when you got back.
Okay.
Here's what I was trying to say. So we started with this adiabatic assumption PV raised to the power gamma equals K. Now I would like to find an expression for this thing appearing in our integral, which is v to the power 1 minus gamma. How should I do that? Well, the obvious place to start is first to divide both sides by v to the gamma, which gives me on the left side simply p, and on the right side, sorry, that's kv to the minus gamma now. So you have this, and then you say, okay, how can I simplify this? But then you say, well, I also have the ideal gas law, which is PV equals NKBT, or in other words, V equals NKBT over P. So now you could just say, okay, why don't I take the top equation and I multiply both sides by the bottom equation? Right, so I'm going to say, okay, I multiply both sides by V at the top, and then I plug in on the left side, I plug in V equals NKBT over P. And when I plug that in on the left side, I'm left with just NKBT. On the right side, I combine the powers, and I'm left with KV to the minus gamma plus 1. So this shows you that KV to the minus gamma plus 1 is the same as N Boltzmann constant temperature. Is that okay? Are you muted?
I do not see how the temperature final and temperature initial follows from that.
Oh, it does. So the derivation I'm doing over here holds for either of the temperatures. So then you would apply this argument separately at these 2 points, right? So you would say it's always true.
Okay.
You got it? Okay.
Yeah.
Good. So then, yeah, we showed that at a particular choice of temperature, kV to the 1 minus gamma is nkb times that choice of temperature. And then I say, okay, apply that once at the final temperature to turn this into a TF. Apply it once with the initial to turn this into a TI. Is that good?
As I mute myself, yes.
Why do you mute yourself?
Because then you won't hear constant scratching from my head moving along the pillow.
I don't mind hearing scratching, but okay. Well, anyway, so we know the answer for the adiabats now, so let's go back and do just some accounting work and write down the work done on each of those 4 legs and add them up. So again, this thing is NKB times the temperature difference over 1 minus gamma. So yeah, I'll use this picture, I guess. So let me fill in the adiabats. So it should be NKBT times the temperature difference. So what's the temperature difference on this adiabat? Well, I think he started at T hot and ended at T cold. So this should be NKB times T hot minus T cold over 1 minus gamma. Right, so that, and again, that's positive because he's expanding on this leg. Okay, so this is, I should try to label these a little more cleanly so we don't lose them, but this is on leg 2. We already computed what's on leg 1, so on 1, this is supposed to be NKBT times, as you did in the DC, the log of, I guess this should be called VB over VA, right, because it's final over initial, and that's again positive. Okay, now what about the negative ones? So I'll do the negative ones in this gold, I guess. So this is an isotherm at the bottom, so we know that this guy should be a negative, negative amount of work, but this is going to get very sloppy now. On leg 3, it's a negative amount of work, and it's again NKT times the log. So I guess this is all at T cold. I should have put T hot at the top. T hot. Okay, and then this guy at the bottom is at T cold times the log of, let's see, V final over V initial should be VD over VC. Is that right? Oh, I have the signs wrong. Oh, this is already negative because it's going to a smaller volume. So VD is less than VC, and the log of a number less than 1 is already negative. Okay, so the minus sign is actually accounted for just by this order, right? Because VD over VC is negative. Okay, but we can just remember that that's a negative number, I guess. And now finally, this last adiabat over here in step 4, well, remember the adiabats well, actually I'm going to put that all the way over here just so we can compare them. But in this step 4, on the adiabats, we remember it's nkb times the temperature difference over 1 minus gamma, but what is the temperature difference, I'll ask you, in this final adiabatic compression?
Thinking. Is it TC minus TH?
Yeah, good. That's exactly it, because remember, he started off this adiabatic compression after pulling from, he's right at the beginning, he's on the isothermal compression at the cold sink. So at the beginning of this, I've just pulled him off the cold sink, so he's at T cold. And at the end, I'm letting him expand and then touching him to the hot sink at T hot, right? So the difference, and we know the work is negative here, right? Because I'm going from right to left. So this has to be a negative number in the parentheses, which means this has to be T cold minus T hot. Now I'll ask you, what beautiful cancellation happens?
I don't know what you're referring to.
Okay, so we're trying to find the total work done in this entire cycle. So the area here, which means we want to add up the contributions along the 4 legs, 1, 2, 3, and 4. I claim 2 of those legs cancel. Which are they?
Are we taking... Okay, each of these legs is the integral evaluated?
Yeah, each of these 4 things,
Okay.
we already did the integrals, right? These are the...
Okay. Let's see. Well, number 4 and 2 are going to cancel out, of course.
Yeah, perfect. That's what I'm getting at. So that's why I did that weird rewriting in terms of the temperatures, so we could see this. Because obviously this is the same overall constant times thing A minus thing B, and then thing B minus thing A. So that's the nice thing. These 2 adiabats cancel. They totally just cancel. So at the end of the day, what we're left with for our total work done as we go around this Carnot cycle is nkb times, we get some positive work from this guy, some positive work T hot times log of VB over VA. And then, I don't know if I should write this with a minus sign to emphasize. Maybe I'll use log of a power to flip the numerator and denominator just so I can write a minus sign out front, because I just want to emphasize that this term is negative. But it's just algebra. So minus T cold log, if I flip this, then I should put the higher volume VC over the smaller volume VD. Because, right, VC is over here to the right, VD is to the left, so that means VC is bigger. Okay, so this is the total work here, right? So this is the total work as I go around the Carnot cycle. And you can see that if we choose T hot larger than T cold, and if we choose VB bigger than VA and VC and VD appropriately, this thing will be a net positive as I've drawn in the picture. So let me go over to this heat gradient. So yeah, here's the answer. The punchline is that since those adiabats cancel, we get this total work for a Carnot cycle which looks like this, which means we've extracted positive work. So the Carnot cycle is sometimes drawn in this cartoon form because basically if you ignore all those steps, the complicated steps in the middle of moving the gas around, and just think of this as a black box, what have we really done? Black box, we had a heat source, extracted some heat Q hot from that heat source, then put some heat Q cold to the cold source, and we got useful work in doing that. So the first time I saw this, I thought this was very surprising because I thought there were some rules or some laws of thermodynamics that you can never turn heat into energy, right? And that's technically true in a slightly different sense. You could never build an engine of this form, a Carnot engine with an ideal gas or anything, that basically just takes T hot, takes the hot bath, and turns it into something which is colder, turns it into a cold bath, and extracts work. You can never cool down a heat source into a colder ice source or something and extract useful coherent work. That violates the second law of thermodynamics, so this is totally impossible. You can never cool something down and use it to power your car. But we can do something almost as good. I find this very, very satisfying, that even though we can't cool down the hot source directly and turn it into work, if we dump some of the heat from the hot source into the cold source, we're basically just allowing the energy to go downhill from the hot source to the cold source, but along the way we kind of charge rent, or we charge a toll to the energy as it goes through and extract some useful work. So it's a very interesting principle, and I mean, there's all sorts of theorems you could prove about this, that this is actually you can prove this is the maximum efficiency for any engine that moves heat from a hot source to a cold source or something, and you can get bounds and lots of stuff. So it's a very rich subject, but anyway, I'm only just scratching the surface with it today. Good. Thoughts on Carnot?
I guess this is also the implication that a larger difference between hot and cold temperatures produces higher energies.
Yeah. The higher the gradient
Which
between the two, the more
applies in real life as well.
Yeah, I'm trying to think of examples where that. Are you thinking of a specific like a biological context, or like in a car, or like where do we use this?
Just in a car, because it's well recorded that in like summer weather you put out less power.
Interesting. That might be for a different reason, because the car isn't a Carnot engine because it's burning fuel, of course, rather than using a heat gradient, but there might be something related in that the heat affects the kinetics of some of that combustion or something. I don't know.
Oh, yeah, that's also likely, which is another case where this thought popped up.
Yeah.
So, there's some reason, I just don't know it.
Yeah, it's probably a complicated combination of reasons, like a lot of real-life problems, but... Okay.
Oh, real-life problems. Monty Hall. Okay. Still not Monty Python, unfortunately.
Sadly, no. But now we're gonna...
Who is Monty Hall? Oh, God.
I think it's some game show something, but...
Oh! I remember what this is.
Do you know this problem?
Is it the would you like to change your choice?
Yes.
Knew it!
You've seen this before.
Yes.
Okay, well, I will ask you the question anyway, but maybe you already know the answer. So.
Well, I can't remember the answer, so...
Okay. Alright, okay. If you haven't already seen it, then I'll actually take my time and do it properly. So, good. So, for context, we're now switching gears completely to probability theory. And the purpose of my including this interlude is to show you that the human mind is uniquely bad at intuition surrounding probability and statistics. So in the next couple sessions, we're going to learn things like Bayes' theorem, conditional probability, and more complicated notions that exist both in the discrete case. By discrete, I mean just some finite set of outcomes with different probabilities, like flipping a coin with heads with probability a half and tails with a half, or rolling a d6. So that's the discrete case, which is simpler. We're also going to do the continuous case, which involves integrals. But because probability is so counterintuitive, I think things like Bayes' theorem and conditional probability with integrals, which our brains are bad at predicting, you can already get people to have serious failures of intuition with just discrete probability. So to introduce that and to kind of show you a fun problem that I think is very cute, we're going to do something that has nothing to do with calculus. It's purely discrete probability, conditional probability, to show why people often, make incorrect assumptions about probability because of the ways our brains evolved. Okay, so here's the setup. So you're on a game show, and the game show host presents 3 doors to you, doors 1, 2, and 3. And he tells you that behind these 3 doors, in some order which you don't know, there is 1 new car and 2 goats, but you don't know which is which. And he says you can pick whichever door you like, and I'll open it and you get what's behind the door. And I'm assuming you prefer to have a car rather than a goat in this setup. So you do the following. You pick a particular door, say you choose number 1. So you say, I want door number 1. And then before opening the door, the host stops you and says, okay, I know you picked door number 1, but I'm going to tell you something. And he walks over and opens door 3 and says, look, behind door 3 is a goat. And then he says, okay, now knowing that door 3 had a goat, you have an option. Do you want to stick with your choice of door 1, or would you like to switch your choice and instead take what is behind door 2? I ask you, is it to your advantage to switch doors?
No.
No, why not?
Because, I think, at this point it's a coin flip. You don't know any information about one or two anyways.
Okay. So here is the incorrect answer that almost everyone says. The incorrect answer is the following. There are 2 doors left, and I know one has a goat and one has a car, so my chances are 50-50, and it doesn't matter whether I switch. It's a coin flip. Like 10 out of 10 people, when you ask them this problem, will say that. I said that the first time I heard this question, but it is dead wrong. This is just total.
Well, good thing I didn't spend any time thinking about it.
That's fine. Wait, are you mad at me for not letting you think longer or something?
It's easier to demand someone think longer.
Well, I mean, okay.
But then that would give away. Okay, I see.
Yeah, I mean, the point of this was not to, make fun of you for getting the wrong answer. It's to emphasize everyone gets this wrong, and let's understand why. So I hope you're not mad at me, but this is what I expected to happen. So I'm going to explain it probably 3 times. I'm going to beat a dead goat with this because it's so incredibly important. So here's what's happened. When you first chose the door, so there were 3 doors, 1, 2, and 3. When I first chose the door, say door 1, at this stage of the game, my probability of getting the car was 1/3. Because I know nothing about any of what's behind the 3 doors, and I only know one has a car. So right now, the probability that I'm going to win is 1/3. Now, that means, by the way, that the probability that the car is behind either of these other 2 doors is 2/3, simply because the total probability is 1. Now the host comes over and says the goat is not behind door 3. Okay. Well, this probability cannot have changed, so it still must be the case that the probability the car is between either door 2 or door 3 is still 2/3 by the sum argument from before. I know it's not behind door number 3, so in fact the probability that it's behind door 2 is 2/3. So it is definitely in my advantage to switch. If you switch, you will be right 2/3 of the time. If you stay on door 1, you're only right 1/3 of the time. I have a picture. Actually, I have several pictures. So let's...
You can basically skip the entire section.
Why should I skip the section?
Because it's clear.
I don't care. I'm literally going to say this 3 times. It's incredibly important. So, okay, here's a picture of the options, basically. So there are, if we label and think of the 3 possible things that could have happened. So there are 2 states of the world where the original door I picked had a goat, and 1 state of the world where the original door that I picked had a car. And these all have probability 1/3. In the first 2 states of the world, when Monty comes over and reveals that one of these other doors had a goat behind it and rules it out, I would have won if I had switched because I originally chose a goat. So here switching wins, and likewise here switching wins. The only way that staying would have made me win is if I had chosen the car originally. And as we know from the first step, you only choose the car correctly originally 1/3 of the time. So here's another picture showing that switching nets you a 2/3 probability of car, staying gives you a 1/3. Okay, another picture. Here's a split with those 3 possibilities again, but now, circling to emphasize what we're doing. So again, if we label the 3 doors in no particular order, car, goat, goat, car, goat, goat, car, goat, goat, only in the world where I chose the car originally, where green now indicates what I was choosing. So if I chose the car originally, it's disadvantageous of me to switch. If I had chosen the goat originally, which happens 2/3 of the time, it is advantageous of me to switch. So in those 2/3 where switching is the right choice to win, 2 of the 3 possible states of the world, switching gets me the car. So switching as a strategy has a 2/3 probability. So you can ask, what is wrong with the argument which people normally give that someone will say it has to be a coin flip because what he told me about, say door 3, which he just opened, can't possibly affect what's behind my door. That's the argument people typically make. But the problem is it's not true, because the host has given you additional information by doing this. He is by actually revealing that one of the other doors has a goat, and he knows that that door has a goat when he chooses to open it. He's actually given you, in a Bayesian sense that we'll make precise later, he's actually given you updated posteriors. He's given you new information about the probability distribution. And to see that...
So, now I have to ask before you go any further.
Good.
What if you came into this problem when there was already a door open?
Oh, so if you walked in... Okay, yeah, good. So if he... and if you walked in and you just see a door open with a goat, and he says, now there's 2 doors left, which one do you want? Then it's a coin flip. Yes. You see why that's different, though. Walking in after he has opened one of the doors, but not knowing the choice the other person made, and he just says pick door 1 or door 2, there it's a coin flip. But if you had walked in after seeing the first person choose door 1, and then seeing Monty's open door 3, and say this one was a goat, and then you walked in and saying that, and then he turns to you and says, instead of the original person playing the game, he says to you, which door do you want? You should still switch, right? That's always true. Good.
It makes sense, but I don't want it to.
Yeah, it's bad for our brains. It's very counterintuitive. The thing that you have to get your brain over is the fact that the host knows which okay. How do I say this? You could ask, okay, here's the objection. This is a version of the objection that I raised when I first saw this. So here's the argument I made, which is wrong. I picked door 1, and then Monty opened door 3 and eliminated it, and now you tell me that I should switch. Are you getting yelled at?
Let me check.
Yeah? What are you doing? I'm in a calc meeting. You need to clean the table up. Yep, I haven't forgotten.
Alright.
Are you okay? Or do you have to go?
No, I'm good.
Okay. Here's an objection that someone could say. Someone could have said, this really should not have affected the outcome, because if it were not the game show host, but a random fucker off the street, if a random person who knows nothing about the doors came in and opened door 3 and showed that it had a goat, and then walked away, then how could he have imputed any information to me by doing that? Right? How does seeing him open the door and see that there's a goat behind that one make me conclude that the probability is now 2/3 for the remaining door? Because this person
is it because that the problem with that argument is probably that there is the chance that that guy opens the door with the car?
Exactly. That's entirely it. Right? Because if a fucker came off the street and opened this door at random, there was a chance that the car would have been behind that door. The only reason I'm getting new information from this setup is because the game show host knows which door has the car, and he is intentionally choosing a door which has the goat. So you know when he opens that door, he's getting rid of the goat, and he knows that the other one either has the car or you chose the car. So only because of the knowledge of the game show host is this giving additional information to you as a Bayesian agent. And I think that what finally got me to understand that is this limiting case. So let's just take a limiting case that makes it much more clear why the game show host is imputing information here. So now suppose there's 100 doors. There's 100 doors with 99 goats and 1 car, right? I pick a door at random, say I choose door number 1. Now the game show host says, all right, you chose door number 1. I'm going to eliminate 98 other doors. Door 2 has a goat, door 3 has a goat, all the way up to door 99 has a goat, and then he leaves door 100 unopened. And then he says, all right, I've eliminated 98 doors that have goats. Do you want to switch? Now you'd be fucking insane to say, no, I'm not going to switch, it's 50-50. Right? Because he just eliminated everything except one other door, which I mean, he knew which door has the car. So by eliminating all of those, we've basically seen that, the probability that the car is actually behind the one door that, with his knowledge, he chose not to open, it's going to be in this one 99 out of 100 times. The only other possibility is that I chose the car by blind luck the first time, which only happened with probability 1 out of 100. So anyway, I find this more intuitive, because when you put in 100 doors, it makes it very clear that, the game show host is really helping you out. He's basically saying, I know where the car is, and I'm going to eliminate all the other goats. So, I mean, the 3-door case just makes it harder for the brain to grasp that, because the numbers are
because it's 2 options. It makes you think of coin flips.
Yeah, it looks symmetrical. And you want to make this argument about how that door 3 can't affect what's behind my door or something, but it's just not correct. Okay, so you're probably wondering...
beating a deep goat.
Oh my god, that was not even intentional. Why am I beating a dead goat? So, as I said at the beginning, this has nothing to do with calculus, but our brains are bad at intuition surrounding...
Monty.
No, that's how it's spelled.
Oh, okay.
Oh wait, did I misspell? No, I thought Monte Carlo. Oh my god. No, it is with a Y. Jesus Christ. I'm confusing Monty Hall with Monte Carlo. Sorry.
Nice job.
Yes. So that should be Monty Hall. Yeah, so the human brain is terrible at conditional probability. So again, as I signaled at the beginning, I'm introducing this in a simpler case because I want to flag how humans are bad at conditional probability before integrals get involved. And there's many studies that most of them involve doctors and test results. People like statisticians will get 100 doctors, medical doctors who make, life and death decisions about patients, and they'll describe some situation to them that says like, oh, you get a test for your patient that is trying to detect whether they have cancer. And, the probability that you get a false positive, right? You have no cancer, but it says it's positive for cancer is this probability. The probability of a false negative, that you do have cancer, but this returns no, is this probability. They give them the numbers, and then they just ask, okay, so, your patient has a tumor, you do the test, and it comes back negative. What should you do? Estimate, pick the answer, basically. And doctors will almost always get these things wrong when there's a correct statistical answer that you can prove mathematically for what the right decision is, assuming some payoffs or something, just because the human brain is so bad at this idea of thinking in a Bayesian way. Bayesian
is one of the cognitive biases, including being close on probability.
Being close. What do you mean by being close?
Like how you were so close to a insert number when you rolled a die.
I don't understand what bias that is.
I think. I don't know. I just keep thinking of how many times it has happened that... how do I word it? For example, I'm playing D&D and someone rolls a die and misses by 1. They say they were so close.
Well, that's not a bias. Cognitive bias means you have to make a prediction, which is wrong. Right, so saying I was so close is just a comment, right? That's not a factual statement. But one example that, here's a real bias that happens that people do in D&D, right? Sometimes people will roll low many times in a row, like they roll a 1, a 2, 1, 2, 2 on a 20-sided die. They roll 3 d20s and get low numbers, and then they grab the die to roll again, and they say, wow, I'm due for a high number. Right, like I've had a streak of low ones, so now it has to balance out. It's somehow more probable that I'm going to get a high roll this time, even though just because my previous rolls were low. That's a cognitive bias.
I see. Okay, I just had the idea that every single chain of rolls is just as likely as any other.
Yeah, they're
a 1, 2, 3 is just as likely as a 1, 21, a 1, 3, 1, so on.
Right, but to put a point on it, the point is that when you go to make die roll n plus 1, that is totally independent of die rolls 1 up to n. You could roll a 1 20 times in a row, and then ask someone, hey, do you think the next die roll is going to be a big number? and they say, yeah, I'm due for a big number because I just rolled 20 ones in a row, so I'm probably going to get like a 19 this time. That's simply false. This has nothing to do with the previous events. The probability of getting a 20 on this roll is still 1 in 20, just as it was for all of those other ones. The fact that you got a bunch of low numbers doesn't mean you're somehow due to get a high number now. That's not a problem.
Of course, this is assuming that your die is not weighted.
Well, yeah, fair die. But anyway, I'm just flagging this. You might want to read. Might post some reading and some DCs. There are certain organizations like the Center for Applied Rationality and these people at lesswrong.com that have kind of guides for how to be more Bayesian in your thinking in everyday life. And it's not especially mathematical, it's not calculus, but it signals a lot of things that we just do wrong, that we're kind of illogical or irrational in the way that we behave in our day-to-day lives. And a lot of it comes from not understanding Bayes' theorem or understanding probability correctly. So
I look forward to reading this.
Okay, that's good. But it's an important takeaway. I mean, this is why I want to focus on probability for a couple sessions, because it's one of the most applicable to everyday life and the way you should, behave and how to be rational just as a human, even outside of mathematics. But anyway, more on that later. Any questions on goats?
Oh, that was the end of the interlude? Okay. Huh. I do not have any more questions about goats or simulating goats.
Okay. I might actually go the full 2 hours. Okay. All right, a challenge for you, finally, now that we were just talking about dice. So suppose I roll a fair n-sided die, could be 20-sided, 6-sided, whatever, n-sided die where n is an integer, and then I divide the result by n. So for example, I roll a d20, divide the number I get by 20, not by the roll that I get. You divide by the maximum number on the die. So if I do that, what are the possible outcomes that I can get, and what are the probabilities? Just list them.
We write the list as the set of numbers 1 over n, such that n is greater than or equal to 1 and less than or equal to... Wait, no.
Yeah, don't use n twice.
I think. Let's see. Say 1 over z, where z is an integer, and in the closed set 1 to n factorial.
N factorial? Why factorial?
I think.
If I roll a 20-sided die, can I get 20 factorial as an answer?
No.
Where did that come from?
So 1 to n.
1 to n, yeah.
Yeah.
Good. Yes, so for instance, it's 1 over n, 2 over n, 3 over n, ... up to the second to last one is n minus 1 over n, and then n over n is 1. Those are the possibilities. What are the probabilities of each of those outcomes? So these are the xi's.
Each of them has a probability 1 over n.
Yeah, so these are all 1 over n, because we're assuming it's a fair die, so they're all equally likely. Good. This is called the discrete uniform distribution. So I plotted it here for you. Here on the y-axis, we're showing the probability of an outcome. So as you say, they're all 1 over n. And these are the numbers from 1 over n, 2 over n, 3 over n, up to 1. So this is sometimes called a probability mass function, PMF, probability mass function, because I'm just plotting these points, discontinuous points, for each of the possible outcomes with their probabilities. Okay, so as you said, yeah, the die returns a number from 1 to n. When you divide, you get 1 over n, 2 over n, up to 1, and the probabilities are all equal. Uniform distribution. Okay, now we want to take the continuous case. So suppose I say the following. Now I'm going to draw a random real number from the interval 0 to 1, closed interval, including the endpoints, such that all numbers are equally likely. So this is somehow taking the limit as n goes to infinity, if you like, in the previous example. So you can get any of the continuum of real numbers between 0 and 1, not just 1 over n's, any number. You can get 1 over pi, you can get 1 over pi e to the 7th, whatever. Any number is equally likely. 2 questions. First question for you, what is the probability...
I'm going to say 1 over infinity.
Good, yeah, so What real number should we assign that value to?
0.
Yes, 0. Good, yeah. Of course, the probability of getting any particular number exactly must be 0, because there's infinitely many numbers and they're all equally likely. Second question for you. Suppose I make a tiny interval whose total length is epsilon, centered around 1/2. So you could view it as this interval here, where this side is epsilon over 2, this side is epsilon over 2. So it's the interval 1/2 minus epsilon over 2 to 1/2 plus epsilon over 2. What's the probability that I draw a number in that interval?
I'm going to say epsilon over 1.
Yeah, good. So probability equals epsilon over 1, and maybe just like one sentence, can you explain why that's true?
Because the size of that is, well, this interval has width epsilon, and the total width is 1. So just I guess it's kind of like a representation of the percentage of the interval made up by epsilon.
Yeah, that's exactly right. So you should think of this basically as saying we're taking, since all numbers are equally likely, we can find the probability of getting this interval by just finding sort of the length of that interval divided by the total length, or in a way that will be slightly more useful for us later, that's the same as saying it's the area under the curve between the strip from 1/2 minus epsilon over 2 to 1/2 plus epsilon over 2. It's that area divided by the total area under this guy. But either of those is fine. In this case, it's much easier to just think about the length of the interval as epsilon and the total length of this interval is 1. Good. Now, question for you. You just told me the probability of picking any particular number in this interval is 0. But then you told me that the probability that I pick some number in this little interval around 1/2 is, say, epsilon over 1, which, I don't know, let epsilon be 0.1 or something. So that's 10%. So you're telling me this interval is made up of individual numbers, each of whose probability of being chosen is 0. There's 0 probability that I choose each number in that interval separately. But somehow if I add up all of those infinitely many zeros, now there's a non-zero probability of getting someone in the interval, a 10% probability. How is that possible?
Counter argument. If the chance of getting something in that interval was 0, then that would imply that there was 0% chance of getting anything in our interval.
That's true. Yeah. So it seems we have a contradiction, because you could apply the same argument to the whole interval. You say, I have an interval from 0 to 1. I'm going to choose any number out of here such that they're all equally likely, but the probability of getting each number individually is 0. So how is it the case that the probability that I get any number whatsoever over the whole interval is 1?
This is the problem with infinity, I assume.
Yes. This is it. This is why continuous probability is very confusing. So just to rehash the answers, yeah, as you said, there's infinitely many numbers in the interval, so the probability of drawing, say, 1/2, a specific number, is 0. And the interval around epsilon with the 1/2 or something, this interval is with the 1/2, so as you said, the probability of getting someone in that interval is epsilon. Now we have to resolve that argument I just made. So here's the answer. When there are infinitely many outcomes, it does not make sense to talk about the probability of any singular outcome, because there's infinitely many of them. The only thing that makes sense is to talk about the density of probability per unit length. Probability per unit length. And this actually isn't that crazy. So let's just go back to the rod example, because we could have had the same contradiction in the rod. So we're assuming this rod is a continuum. I mean,
I was noticing a thing with my logic where if you have infinitely thin strips, they'll have 0 mass, and it somehow sums to a mass.
Yes, exactly. That's the problem. Because, we're ignoring that this thing is made of atoms. We're assuming this can be subdivided into infinitely tiny strips. So it's basically saying this thing, each of these, as you take the strips infinitely thin, it's basically like in the rod, it's just a point, right? Because this thing's one-dimensional. So you'd say the mass at any one of these points, mass at a point x, is 0. But of course, if we integrate across all of these, we get a non-zero mass, the integral of the density. So the error in doing this, the incorrectness in the argument that the total the total probability has to be 0, because the probability of each individual number is 0, is simply a confusion about the order of taking limits, right? Because we're effectively taking, when we do an integral like this, we're taking the limit as delta x goes to 0 of some sum of, some function evaluated at an xi, delta xi, from I equals 1 to n. And we know that if we take this limit, there's two things that are changing at the same time. One is that the widths are getting smaller, and two, the number of terms in this sum is getting much bigger. Capital N gets larger if the strips gets tinier. So there's two competing effects, and of course they balance out to give some finite answer in general. The fallacy, the cognitive bias here, is to ignore the fact that the sum is getting more and more numerous and just take the limit and apply it to this delta x and say, oh, delta x goes to 0, so they're points or something, so they have no mass, density and length. So that's the cognitive bias. And I'd just like to show you a comic very quickly. Gene 014, which
I was expecting XKCD, honestly.
No. So this is a little, you can read at the top, it says the importance of understanding infinitesimals. And it has this guy at a lemonade stand, a little kid at a lemonade stand. And he says, how much is a drop of lemonade? The kid asks for a drop. And the guy says, I'll give you a drop for nothing. And the kid asks, can I get a cup full of drops? Because the price of one drop of, of 1 point in your probability distribution is 0. Then you would just ask for the whole cup full of drops and get it for free. So anyway, maybe you're not as amused by that as I am.
I'm grinning, but I'm not laughing.
Okay, log smile. Alright, so let's just do the definition. Enough fucking around. So, definition, let f of x be a real valued function with the following two properties. One, all of its outputs are non-negative, so this is probability can't be negative. So probability can't be negative. And it has the second property that the integral of this function over the entire real line is equal to 1. So something has to happen. The total probability must be 1. One of the outcomes happens. So in this case, we say that this function f of x is called the probability distribution, or sometimes the probability density function, or PDF, a probability distribution for a random variable x if, when you generate one instance of the random variable x, right? You roll the die or run the code that generates some random variable. If when you do that generation, the probability that your generated output lies in some interval between a and b is the integral of f of x between a and b. So this is the definition. It's a probability distribution. Non-negative integrates to 1, and the probability of getting an outcome in any interval is just the integral of the PDF over that interval. That's what we mean. Okay, questions on the definition?
I do not have any questions.
Okay, good. Let's do a challenge then. So the most important distribution in all of probability and statistics is the Gaussian, or the normal distribution. And I write it like this on the left side. This bar is just to indicate that x is the random variable. So this is the thing that this is generating random instances of. And mu and sigma are parameters. So they just change which Gaussian you're talking about. They change the shape of the Gaussian. So mu is something called the mean, or the average of the Gaussian. Sigma squared is called the variance. And sigma itself is the standard deviation, basically, which we'll prove later when we define that. So anyway, here's just some pictures. The blue one has the mean, which is the average being 0. So you see it peaks at wherever mu is, right? This guy peaks at 0, and sigma squared controls the spread. So this blue guy has a spread of 0.2, so you can see he's pretty skinny. The guy at the bottom, this yellow guy, he also peaks at 0, but he has a spread of 5, so you can see he's much fatter. So those are the two parameters. Now I'll ask you, usually when you write this down, there's a very specific number that appears here, but I've removed that number and called it n. So now I'll ask you, what can we do to figure out what n must be in order for f to satisfy the definition of a probability distribution?
Well, it's certainly it's certainly greater than 0, but I need to think more.
Yeah, that's one of them. What's the other thing it has to have?
Just tabs back without any explanation.
Yeah.
Probably because there's something here.
And what must be true if it's a probability distribution?
I'm reading and I'm thinking about how to apply things.
I mean, there's only one equation that's really useful for us here, right?
There's 2, but I'm looking at the top one.
Yeah, this condition, right?
Oh, I think.
Right? The integral has to be 1, right? Total integral.
Yes.
So that gives us an equation, because if we integrate this function from -infinity to infinity, it's going to give us some answer that depends on n. So why don't we just do that and set it equal to 1, right?
Yes.
Okay. All right, so let's do that integral. So integral from -infinity to infinity, n e to the minus the quantity x minus mu quantity squared over sigma squared dx. What should I do?
I think we can pull the n out, assuming it's constant.
Yeah, and it is. Good.
And we need to... I don't know if we can evaluate... I think. I'm thinking about if we can evaluate this integral.
We can. A u sub might be helpful, though. Let me just as a
Yes.
If it were instead, if it looked a little different, if it were the integral of e to the minus u squared du from -infinity to infinity, what would that be equal to?
Square root of pi.
Yes. So can you make a u sub so that this thing in the junk looks like minus u squared?
Let's let u equal...
Oh, sorry, I forgot a 2. Sorry, there's a 2
I
down.
think.
Here we go. My bad.
I believe that we can let u equal x minus m over root u sigma.
That's a mu, but yeah. X minus mu over, you said root 2 sigma, is that right?
Yes.
Good, yeah. Alright, so then what's du and how do I do the integral then?
Du is going to be, let's see, 1 over root 2 mu.
Root 2 mu. Why mu? Mu's a constant, right?
Wait, then what's sigma?
Mu and sigma are both constants. X is the only variable here.
Okay, I thought you were telling me that sigma was mu. I meant sigma.
Sigma. I don't understand what you just said.
When you said that what I was trying to say was mu, I assumed you were talking about the thing in the denominator.
No, this letter is sigma, this letter is mu.
Sigma. 1 over root 2 sigma.
Oh, now I understand. Okay, yeah, so you knew the right thing, but you were using the wrong word for it because I confused you. Okay, now it makes sense. Alright, that's correct. Now, how...
Well, times dx, of course.
Oh, yeah, fucking, how did I just do that? Good. So then what does our integral turn into?
It becomes n integral from negative... Well, let's see. Does anything change? No, it's still massive and / or massively negative at each point.
Yeah, because all we did was shift it by a small finite number and then divide, but that doesn't change anything, right? Good.
Yeah.
Okay, so then what's this?
Becomes e to the negative u squared times root 2 sigma du.
Sigma du. Good. And what's that?
And we pass the root 2 sigma through to get n root 2 sigma I evaluated. Well, yeah, n root 2 sigma times root pi.
Good, root pi. Okay, and what must this be equal to for a probability distribution?
Which must be equal to 1. So, n equals 1 over sigma root 2 pi.
Yeah, so we solve n is, that's a shitty equal sign. N equals 1 over sigma root 2 pi, with the pi under the root, right? Good.
Correct.
Very good. And indeed, if you've ever looked up the bell curve or the Gaussian distribution, even on Wikipedia, the normal distribution or something, so if you look up the definition of a bell curve, you will always see in front of it this funny factor. Sometimes they put the sigma into the square root and make it a square, but it's the same as what you just told me. You always see this prefactor out front, this 1 over root 2 pi, sigma squared or sigma outside the square root. So if you're ever wondering where did that come from, why does that number appear in the bell curve, it's just because when you do the integral, and you have to have memorized that the integral of e to the minus u squared from minus infinity to infinity is root pi, it's very important. Once you've done that, this must be the prefactor. Good.
Why does it always end up as u and not x?
Why does it always end up as u? What do you mean?
Like whenever you talk about e to the negative u squared from negative infinity to positive infinity.
Oh, I mean, well, in this case, just because we did a u sub. I don't know.
Like, you always see it as the u instead of an x.
I see x sometimes in, for instance, one of my favorite pages on the internet, list of integrals in quantum field theory. If you go to this page on Wikipedia, common integrals in quantum field theory, you will see a lot of e to the minus x squared integrals.
That is a lot of...
e to the minus ax. I love how they list slight generalization, e to the minus 1/2 ax squared e to the minus 1/2 ax squared, e to the minus 1/2 ax squared plus a jx, e to the minus 1/2 ax squared plus ijx. Like, it's so much shit. Alright, I'm wasting your time, I apologize. Yes.
Adjusting headphones.
Good, okay, so, yeah, as you said, we set this integral equal to 1, did the change of variables, got n root 2 pi sigma, which must be 1, and that gives us what n must be. Good. Okay. Another example, you might ask, okay, have you seen this in chem yet?
No, but I'm saying it's more challenges.
Yeah. If you don't want to do it, I can solve this one for you, but...
I'm not complaining.
Okay. Okay, the motivation is, you could say...
Where do what? Where do PDFs come from? What?
The word I just defined for you a moment ago, probability density function, right?
Oh my god.
Probability density functions. What did you think it's doing?
Who writes all these papers?
Come on. Okay. Good, so you might ask, okay, well, you just handed that Gaussian. Did you pull that out of your ass or something? Where do PDFs actually come from? One source, which we'll do in this problem, is from quantum mechanics. So as you know, in quantum mechanics, when you measure something, you collapse the wave function into one of several possibilities, so the result of your measurement is not deterministic ahead of time. It follows some probability distribution. And as you can prove, if you want, I can derive this for you sometime, if you have an electron in the ground state of hydrogen, in the ground state like n equals 1, right, which you've been studying recently, and you ask, I measure the radius of the electron, how far away it is, the radial coordinate from the nucleus, and ask what is the probability distribution for what distance from the nucleus I find it at. So the radial PDF that you get from quantum mechanics looks like this. It's 4 over a0 cubed. Do you know what a0 is, the Bohr radius, the Bohr radius?
Yes.
Okay. Yeah, so it's 4 over a0 cubed times r squared e to the minus 2r over a0. So now I'll ask you, what is the probability that I find the electron between two radii, say r1 and r2?
Well, it says to integrate.
Yeah.
So we want to integrate from r1 to r2 of, let's see, let's factor out a 4 over a to the, 4 radius cubed.
Yeah, 4 over a naught cubed comes out. Good. I'm going to write that a little nicer, but you can keep talking if you like.
Yes, I think. About potential use-ofs, if any. Well, Yeah, never mind. Oh, I don't know why I was saying never mind. I was just thinking u equals r squared. See, it's u-r. Oh, wait, it's in the exponent.
Yeah,
never mind.
It's the wrong way. If it were r squared here and r down here, that would be perfect, tasty sub. It would be begging to be a sub, but it's in the wrong place.
Freezing! What do you think? Well, it looks like we could just keep moving derivatives onto the...
Yeah.
Don't know whether we move it onto... Yeah, we move it onto the e to the power of jazz.
Well, you want the derivatives to hit the r squared, right? Because you want to keep flattening it.
Yeah, okay. That makes more sense. That's what I was going to say originally, then I realized... Then I was thinking about how e to the x equals... Well, integral e to the x equals c to the x and all of that stuff.
Yeah, but then this guy would be getting bigger. You'd have r cubed, r4.
Yeah.
Alright, so I'll do the first one. So when I move one derivative, what do I get?
We move it on to, well, 4 over Bohr radius cubed times, I think, 2r times... Wait.
No, in the brackets, this guy isn't differentiated yet, right?
Oh, yes. So it would be r squared times, I think.
R squared times the integral of this guy, right?
Yes, just recalling. It would be e to the negative 2r over Bohr radius times negative 2 times Bohr radius.
Times integral, so times negative a, the inverse of that, right? A0 over 2, right? Right, because I'm integrating e to the minus 2r over a0. So when I integrate...
Right, this is... I forgot that we were not moving the derivative onto it yet.
Yeah, so it's this thing evaluated at r1 and r2 minus the integral of the moved guy, so what do I get for this one?
The integral is going to be from r1 to r2 of 2r e to the negative 2r over Bohr radius times negative 2 over Bohr radius. Unless I'm still getting things wrong.
Bohr radius over 2.
Probably am, so it would be Bohr radius over 2.
Yeah.
Because I can't integrate, right?
Yeah, you want to divide by this thing, so...
We aren't moving derivatives onto e to the jazz.
Okay, but good, that's fine. So now we need to integrate by parts one more time to move it onto this thing. If you're getting sick of this, let me know and I can just show you the solution slide, but if not, what should I do next?
Move the derivative onto it, and let's see. Oh, you're writing over there.
Yes, I'm running out of space, but yeah. So I'm going to go ahead really quick and simplify. I'm going to pull out the minus a naught over 2 and make this a plus.
Oh, yeah, that works.
Just to make your life a little easier, but okay. So then you can tell me, what do I do with the rest? I guess I should get rid of the 2 as well, right? Because the 2's cancel.
Okay, and that stuff there is equal to begin parentheses, or begin bracket, r times e to the negative 2, well, r times e to the negative 2r over a naught.
2r over naught, good.
Which is then times, I'm gonna write this time.
You got this.
It would be, yeah, negative 2 over, no!
That's the derivative. You want the integral.
A naught over negative 2, or negative a naught over 2.
Good. R1 to R2. Alright, good. Then what's left is what? I think we could just do this in one step and just write down the answer. So when you do the last part, it's the integral of What?
integral of from R1 to R2 of e to negative 2r over a naught times negative a naught over 2.
Times negative a naught over 2. Okay. Okay, now I'm running out of space, but I'm going to pull out the minus a naught over 2 and combine it with this a naught to get a plus a naught squared over 2. A naught squared
Yes.
over 2. And then I think this integral is pretty easy, so what does this thing become?
And that is then e to begin brackets e to the negative 2r over a naught times negative a naught over 2.
Good, you got it
And
right this
brackets
time.
from r2 over r2 to r2 minus r1 or whatever.
Yeah, I'm not going to write all those out, but yeah, so good. It's a sum, as you say, of 3 bracketed terms. Let's just look at what the structure looks like. The first bracketed term is basically r squared times the e thing times an a0 with some number. So this guy has 2 powers of r, 1 power of a0. The second guy has 2 powers of a0, 1 power of r times the same exponential. The third guy has 3 powers of a0 and no powers of r. And they're all with some numbers, right? Good, so let's just compare that to the solution. I think, yeah, you do the same integration by parts thing, you still have the whole overall over, what do you like?
The probability has to be 1. The electron has to be somewhere.
Yes. Yeah, probability distributions should integrate to 1. Good, yeah, so integrating by parts twice, you end up with something that has an overall exponential prefactor, and then 3 terms that have different powers at a0 and r. So an a0 r squared, an a0 squared r, and an a0 cubed with some numbers. Okay, and you could do similar integrals to find where the electron is in other states, but I don't know. I just found this very satisfying the first time I did this calculation, because when I was first taught in high school chemistry how electron shells work, it just seemed like it was handed down by God. It's like, these are the orbitals, they are n and l, and there's quantum numbers, and this is what they look like and their shapes, and it looks like someone just invented it, but it's, I don't know. It was very nice to actually see that there's actual equations you could put on this. You could say very precisely the probability that it's in any region I want. I just evaluate this number. I don't know. Were there any problems about this sort of probability distribution stuff in 3091 so far? No?
No, we never really talked about the problem. Well, we didn't talk about the formula. I can't even remember if we talked about the formulas of the probability.
It's a little disappointing. Well, if you follow the thing in Evernote and do PChem senior year, I guarantee you'll see this. Okay, last thing in the last 15 minutes or so. Now I want to talk about average value or mean value.
I thought that said D6 and not D4, so I was like, how did you get 5/3 when everyone knows it's 3.5?
Oh, fuck. You know what? I started with D6, so that's why it's 1 over 6, and then I changed it. I decided I wanted to change it to a D4, but I didn't change all the denominators, so I really screwed up here. Sorry. But yeah, if you wanted, let's do the D4, let's do it properly. So if you wanted to get the average value of a D4 roll, what's the idea of what you do? Well, the idea is just take the probability of each roll, which should all be 1/4 before I changed everything. 1/4 of the time you get a 1, 1/4 of the time you get a 2, 1/4 of the time you get a 3, 1/4 of the time you get a 4, which means altogether we have 1 plus 2 plus 3 plus 4, which is 3 plus 3 is 6, plus 4 is 10, which is 10 over 4, or 5 over 2. So this is the idea for a simple discrete case, that if you have a bunch of probabilities associated with different outcomes, you just take a weighted average. So this might sound kind of reminiscent of something else, but let me just say it again. If you have a list of outcomes, x sub I, with probabilities p sub I, the average, or more precisely, the expectation value, is defined as follows. Expectation value is the sum from I equals 1 to n of the probability of outcome I times the value of outcome I. Right? In this case, all the pi's were a quarter, and the xi's were just integers. So it's just adding up the different outcomes weighted by their probabilities. Good.
So I have to check. For example, the sum of 2 D4s would that be, would the average of 2d4s be equal to twice the average of a single d4?
Yes, because they're independent events.
Okay.
We can prove this. Well,
Oh yeah,
expectation
that's how
value
sums work.
Yeah.
You can split them.
Expectation value is linear. I mean, this is kind of a hacky proof because, I mean, the statement is really, the thing that I should really be proving is that those two die rolls don't affect one another, that they're unconditional. But, I mean, that's just a physics question. There's no spooky connection between your dice that they influence each other or something.
Quantum dice.
Quantum entanglement.
That would be the worst way to play.
Yes. Okay, is this expectation value just weighted average thing clear? Questions?
Yes.
Okay. Alright, so, I mean, it's probably pretty obvious to you by this point in the game how this is going to generalize to a probability distribution function. So, as you've seen, whenever you have something that involves a sum of some functions, here the probabilities were discrete, this is going to be replaced by the probability density function f, and the outcome is going to stay the same. It's just the outcome x is now continuous, so it doesn't carry a discrete label I. So definition, let f be a probability distribution. We say that the mean, or the expectation value, or first moment, these are all synonyms that mean the same thing, just means basically the average, quote unquote, but I prefer to call it the expectation value. So the expectation value e of x is defined as the integral from minus infinity to infinity of x times the probability distribution f of x. That's all it is. It's a weighted average. And now you see the analogy with center of mass becomes painfully clear, because this is exactly the same formula as what we would have written down for x center of mass, with the probability thing being replaced by lambda, the density lambda. So if you prefer, you can think of the expectation value, or average of a probability distribution, as being the point on the x-axis where that PDF would balance, right? This is the familiar beta. You remember the beta function from the gamma function stuff? We're going to see that beta reappears when you do probability. But here's a particular beta distribution, and you could find its expectation value, which you can prove that, integral of x times beta with some parameters or whatever, you just do this integral and you get this answer, which means this is the expectation value. And you can see it's pretty clear visually that that expectation value is basically like the weighted sum, like where you would balance this thing on your finger if you were trying to hold it up. Okay, is that clear, or questions on expectation value?
I do not have any questions.
Okay. All right. Well, here's another. I signaled before, if you ask where do probability distributions come from in real life, some come from quantum mechanics and some other ones come from StatMech. So here's one from StatMech, which you may have heard of actually when you were doing ideal gases. If you have an ideal gas of particles with masses m at temperature T, their velocities are random, and in particular their speeds are random. So when I'm writing v here, I don't mean the vector velocity, I just mean the size of it, like just the number in meters per second. How fast is this guy going? So those speeds are randomly distributed, which means that there's a probability distribution. There's a function that tells you the probability per unit length in speed space, how likely a particle is to be chosen with that speed. And
is this at all related to the speed of sound in that atmosphere?
No, totally unrelated.
Okay, just random thought.
Good. I could derive that for you too later if you want, but that's not this.
Oh boy.
Okay. So the answer you get is something called this Maxwell-Boltzmann distribution, which if we have time in this chapter, although there's a lot of shit I want to do, I can actually prove this for you, derive this very quickly using the canonical ensemble, not the microcanonical ensemble. But let's just look at what this is. This is very close to something you've already met. If it were just this e to the minus roughly v squared, it would be a Gaussian. But it's not a Gaussian, because there's a v squared multiplying it. So this is basically, it forces it to be, I don't know, it shifts it a little bit. Here I'm showing some plots of it just to try to argue for what it looks like. But basically, since the v squared, it forces it to go to 0 at 0, right? Because the v equals 0 here. And then the exponential wants to kill this off and drive it to 0, but the v squared is getting big for a while. So there's a while where the v squared wins and it gets bigger, then it hits a peak, and then the exponential wins and it just dies off. So all of these have a peak and then a long tail. And I plotted them for different gases. You say, why is this different for different gases? Because they have different mass, right? Mass appears explicitly in the exponential and in the prefactor. So the mass controls basically how fast this thing dies off. For something relatively light, like helium with a small mass, which is the blue curve, you see it dies off very slowly, right? Because it's easy to make those guys run fast because they're very light. But for some heavy fucker like this xenon, probably some isotope, it peaks very low in speed space because it's hard to get these guys moving fast because they're heavy fuckers. But anyway, okay, Maxwell Boltzmann. Exercise for you, which I can maybe just skip and show you the solution because we're running out of time, but it's going to be another integral. I don't like writing out all this shit because there's a lot of letters, so I'm going to make a little b. I'm defining a shorthand b to save writing. In terms of that b, if you just plug in b for this term and the guy up here, you just rewrite the thing on the previous slide like this. It's 4 pi times this shit, b over pi to the power 3 halves, v squared, e to the minus b v squared. Now, what if I ask you to find the quote-unquote average value, or really the expectation value of the speed? What integral would I have to write down to find the expectation value of the speed in this ideal gas?
I'm thinking. Will it be the integral of v times fv, or something else? Okay.
Yep, that's the definition. Good.
dv, of course.
Yeah.
Equals, let's see, 4 pi times b over pi to the power of 3 halves, begin integral, v squared v cubed,
yeah, good.
Exponent, negative b, v squared. And we have integration reports again. Oh boy. You know, if only the powers were reversed.
Yeah. If it were a cube up here, that'd be better.
I need a second to plug in my computer, otherwise it's gonna die out of nowhere because I'm too focused on other things. And now I am plugged in. Let's see. Integration of parts. We're going to continually move on to the v cubed.
Yeah.
So this starts by being equal to. You could just define that part as a constant as well.
Yeah, alright. Maybe
like k.
I'll call that k. Sounds good. Alright, k.
Let's see.
What's the first piece? So you want to move a derivative onto the v cubed, you say, right?
Yes. So it would be, I think, v cubed times e to the negative b v squared times, let's see,
gonna run into
we're integrating, so you need to divide. So would we divide by, I think, that is a v squared in there. I don't like that.
Can't do it. We have to do a trick first. You're gonna have to change variables. It's because we want this to be an e to the, something to the first power. Because integration by parts doesn't work if this is a square upstairs, right?
Yeah.
Good. So if we do u equals v squared.
U equals v squared.
What is
and du equals 2v.
dv, good. Okay, so what is this in terms of u?
Let's see. We are going to rewrite that as, well, I think. Just u.
Yeah, so it's a u up top. Good. What do I do with those?
Yeah, and we need to, down at the bottom, we're going to have, let's see.
Well, if we solve for
yeah,
dv,
solving for it, dividing by 2.
Good. The 2v, right? Because it's 2v.
Yeah, divided by 2v.
So that kills one factor of v here, and we're left with v squared, which is u, right?
Yeah.
Good.
Okay.
Good. is v squared, which is u. So actually, this makes it much easier because we only need to integrate by parts once this time, right? So the change of variables helped us. Okay. So now what? Actually, I'm going to take this 1/2 and put it in with the pi, so I don't have to carry it. But okay, so this is the same thing we did a moment ago. So what do I get for this guy?
Okay, so it's going to be u times, well, yeah, u times e to the power of negative bu divided by, well, times 1 over negative v.
Yeah, good. But I claim something nice happens. Before even moving on to the integral, what happens to this term when you plug in the big boy endpoints?
At infinity, it goes to 0 since e to the negative jazz goes to infinity much larger, well, goes to 0 much quicker than u goes to infinity.
Mm-hmm.
And at 0, we are going to have 0.
Yeah, good. At infinity, indeed, it dies off because this guy's dumb, so he just fucks over that u. So this whole term goes to 0, in fact, which is very nice.
Inhale.
Sorry. All right, then what's the second piece?
The integral from, well, the integral negative bu, well, e to the negative bu times negative 1 over u.
Well, 1 over b, right?
Oh, yes.
Good, so I'm going to pull out the 1 over b, and then that integral I think is very easy to do. What is the value of that integral?
The value of that integral is e to the negative bu times negative 1 over b.
Good. Evaluated at 0 and infinity, and then at infinity it goes to 0 again. What happens
at 0? It goes to 1. Wait, no. It goes to e to the negative b.
This goes to 1, but we still have the second piece. Right?
Okay, that goes to 1, and that goes to infinity.
1 over, I don't know.
Or negative infinity. No? I think.
U is going to 0, not b. B is a constant.
Ow. That goes to negative 1 over b.
Yeah, but it's top endpoint minus bottom endpoint, so when you take the minus of the negative 1 over b, it's just 1 over b, right? Good.
Okay.
Good. So I think we have a 1 over b squared, actually, because there's an overall 1 over b here, and you say we get a 1 over b from this integral, and then there's a k outside, which is supposed to be 2 pi b to the 3 halves, or b over pi to the 3 halves. So
I think what happens in like these live challenges is I go quicker than I should.
That's fine. As you can probably tell, I'm trying to make you think faster. I don't know if it makes you uncomfortable, but I'm always trying to apply pressure in the live challenges so you can make you think fast. That's just because I am what they call a douchebag. I think we did this right, though.
Also interchangeable with normal teacher.
Yeah, well, I don't know.
Oh, wait, good teacher. Wait, no, there's multiple definitions. I don't know,
man. But as you said, yeah, the integral basically, you get that 1 over b squared from that part, and then when you combine it with this 3 halves, since this is a 3 halves, we can turn this into a square root.
You sure you didn't move a half onto that 4 pi before?
Before. Oh. Yeah, I put it into a square root of 4
okay,
2.
Yeah.
It's just nice to write it all under a square root.
Yeah.
Okay. So this is the expectation value of v. Okay. Good. So this is the sort of expected speed you would get for a gas in an ideal gas if you draw one. Now for the final thing, I'd like to highlight one other confusion that people often have about statistics and probability distributions, which is confusing mean and mode. So here's a totally different question. Suppose again we go back to this probability distribution, and I put in this b, and we know what this distribution looks like, right? It peaks somewhere, and then it falls off. And what we just found a moment ago was sort of the average speed, which is going to be actually shifted a little bit to the right because of this long tail. A totally different question you could ask is, what is the most probable speed? By most probable speed, I mean, what is the maximum of this function, the point at which the derivative is 0? So
let's grab our expectation. I think we're going to find when the derivative of our expectation value is 0.
Not the expectation value. We want the derivative of the probability distribution to be 0. So
That's going to be ugly.
no, you could do it once.
Well, no.
So what's f prime? Let's call this whole thing up front C.
Yeah.
So
F prime of v equals c times v in parentheses. Let's see. 2v times e to the power of negative bv squared plus v squared times e to the negative bv squared times... Well, are we allowed to do that because it's squared in there? Or are we handling that?
well, you should multiply by the derivative of the inside, right? Just chain rule it.
So, well, oh yeah. Times negative 2bv.
Good.
2bv or not, oh god.
Puns. Okay. So we set that to 0. Now the nice thing is you see this huge fucking constant out front didn't matter because we can divide out by c. We're going to... Obviously there's going to be an issue at 0, so the point we're looking for is not 0, so we can divide by v and assume v is non-zero. So right away I'm just going to divide by c. We see we can divide by the e to the minus bv squared, because that appears in both terms, so that goes away. We can divide by 1 factor of v, so this goes away. And now we see this equation simplifies dramatically.
Oh, did you pull a... Oh, never mind.
I could divide by 2 as well if you want. Then there's just a
1. Oh, that's what I was suggesting.
1. Okay.
But that does work.
So now this is 1 equals bv squared, or v
square root of 1 over b. Okay.
Yeah.
I mean 1 over root b. There we go.
Yeah. So this is very interesting. Let's just compare this to the number that we got before. Because before we got, basically, this is also proportional to 1 over root b. But let me just separate out the number so we can see roughly what the number is. So square root, this is why I put the 4 in, by the way. So this is root 4 over pi. Now 4 over pi is about 3. So root 4 over pi is like 4 over 3, which is a little bigger than 1. So this is roughly this times... 1 over root b, and say this is like, I don't know, 1.1 or something. So this justifies the thing that I said a moment ago, because the place where the speed is most probable to be, which is, as we just found, is 1 over root 2b, is not the same as the average. The average or mean or expectation value is a little bigger. It's root 4 over pi times 1 over root b. So whenever you're talking about these so-called measures of central tendency in statistics, by central tendency I mean things like the most probable or the average or whatever, you should always be very clear about what your metric for central tendency is, how you're defining what it means to be like the average or middle. Because, I mean, you don't even need calculus to understand this problem. You can ask the question of, like, what is the average number of testicles that humans in the world have? Right? What is the average number? I mean, it's probably a little less than a half because, some men only have 1 testicle, some men have 0 testicles, but on average it's half and half. On average it's like half people have 2, half have 0, so you'd think it would be around the average being 1 testicle, but it's probably a little less, right? So on the one hand, the expectation value of balls is like, approximately 1, but a little less. That's the so-called average, but that's not the most probable, right? Obviously the most probable, I think there's slightly more women in the world than men, most probable is 0. So, anyway, I know I'm going over about this rant, but this is just another thing, another cognitive bias I want you to be aware of. There's several measures of, let's see, I want that Maxwell Boltzmann again. There's several measures of central tendency. Use the one which matters for the problem that you care about. It could be this expectation value. Can't find the picture I want. There's one other called root mean squared. Root mean squared.
Necessary image in Discord.
What was the... Which comment was that in response to, by the way?
That was in response to the... I can't even remember anymore. I think it was the most probable.
Oh, the most probable number of testicles, you mean?
Yes.
Okay. Here's a picture that I should have... And I'll actually stop with this, I promise. Here's a picture I should have included with Maxwell Boltzmann. So here's Maxwell Boltzmann, again. And they are labeling now 3 different measures of central tendency. So as we just found, the most probable speed, which is the peak of this hump, is actually smaller than the mean speed, which we got from doing the integral, which itself is smaller than something called the RMS speed, or root mean square. What does RMS mean? RMS means you take the average value of the square of the speed. So you average value of the square of the speed, and then take a square root of that. So naively, you might think, oh, if I take the average value of the square of the speed and take the square root, that should be the same, right? That's, it's the same as just the average value of the speed itself. But that's obviously true, because obviously not true, because taking a square root does not commute with integrating, right? So this is very different. So anyway, I will end on this note that one of the major confusions in statistics is not paying close enough attention to what measures you're using for central tendency or spread or other important things about your system.
And has this affected you in the past?
Oh yeah, I mean, obviously in finance you have...
Knew it.
But anyway, so... Woo, we made it for the whole 2 hours.
Whoa, actually